Let's suppose we have the following bridge, a three-dimensional bridge, but we're only looking at the two-dimensional side. We're looking at the side view of the bridge. Now we have a beam that connects point A on one edge and point E on the other edge. And this beam is supported by a truss system, a network of rods also known as struts that are connected at the joints at points A, B, C, D, and E. Now all of these triangles are equilateral triangles, meaning the angles are 60 degrees. Let's suppose we want to determine the tension or compression in strut AB as well as strut AC. Assume the bridge is 70 meters long and supports a concrete road of mass 2 times 10 to the 6 kilograms. So because the mass of the concrete road is much higher than the mass of the struts, we can neglect the mass of the struts. In other words, we assume that the mass of the struts is 0. So that will allow us to assume that the forces, the tensile or compressive forces that exist in any one of the struts points along the length of that strut. And that will become important in just a moment when we're describing the force diagram at point A. Now, before we go into that, notice we're only examining the side view of the bridge. The bridge is a three-dimensional bridge and is actually composed of 2 of these trusses. So we have this beam and 2 of such trusses. So we're only examining one of the trusses, and that means we have to examine only half of this mass. So our actual mass we're going to consider, this mass M, is 1 times 10 to the 6 kilograms. It's half of this quantity. Now notice when the bridge is in place, the bridge is stationary. It is in static equilibrium. And that means the net force acting on the beam along the y-axis is 0. So the sum of the forces acting along the y-axis is equal to 0. We choose going upward to be positive, going downward to be negative. So this beam has a certain mass because it has the road, the concrete road that is placed on top of that beam. And so the force of gravity will act at the center of mass of that beam at point C. And it will have a quantity m times g, where m is half of this quantity and g is simply 9.8 meters per second squared. Now, each of these edges will create a normal force that will act at point A and point E. So F and F have exactly the same magnitude. So we have 2F points upward minus m times g, which points downward. So we can set F equal to m times g and bring the 2 over, and we get F is equal to m times g divided by 2. This will become important in the second part, so let's label this equation as equation 1. Now, in order to find the forces acting on strut AB and strut AC, we have to examine point A. So let's draw that all the forces acting at point A. So we have 3 forces acting at point A. We have the normal force F, which is shown here, and we also have the tensile and compressive forces acting on the 2 struts. So there is a tensile force that's acting on strut AB, and it points along and outward of the strut AB. So it points in this direction. This is force AB. And there's a compressive force that points along strut AC and inward. So it points in this direction. And because this is a 60-degree angle, the angle separating force FAC and FAB is 120 degrees. So this angle between the x-axis and this vector is 60 degrees, and that will become important when we're calculating the force FAB and the force FAC. Now, the sum of these forces should sum up to 0 because point A is at static equilibrium. So the sum of the forces acting along the x-axis is 0, and the sum of the forces acting along the y-axis is 0. So we choose going this way along the x-axis positive and the other way to be negative. So force FAC is positive, and force FAB multiplied by cosine of the angle 60, where once again the angle 60 is this angle between the x-axis and this angle, this vector FAB, is equal to 0. And the sum of the forces acting along the y-axis is equal to, well, we choose up to be positive, so we have F minus downward is negative force FAB times sine of the angle 60 is equal to 0. So we take equation 3, which is labeled here, and we solve for F. F is equal to FAB multiplied by sine of the angle 60. Now, we know what F is from part 1. We just simply have to plug in our quantities to solve for F. So we can use this equation and solve for force AB, and we see that force FAB is equal to force divided by sine 60, where force is simply mg divided by 2. So we have mg2 sine 60. We plug in mass of 1 times 10 to the 6 kilograms, half of this quantity, multiply that by 9.8 meters per second squared, and divide that by 2 times sine of the angle 60, and we get a quantity of 5.7 times 10 to the 6 newtons. So this is the tensile force that exists in strut AB. Now, what about strut AC? Well, we can use equation 2 to solve for force AC, which is the compressive force in strut AC. So FAC is equal to FAB times cosine of the angle 60. Cosine of the angle 60 is simply 0.5. So we multiply 0.5 by this force, this tensile force, and we get 2.85 times 10 to the 6 newtons is the compressive force that exists in strut AC. And the force in the tensile force in strut AB is 5.7 times 10 to the 6 newtons.